Good morning, calculus.
Hey, good morning, Doug.
Good to see you all. I just asked my wife if she wanted to skip her walk to listen to a riveting lecture on Euler's method, and she said no immediately. I said, "Do you want to think about it a little first?" And she went, "No." I don't know what's coming to this world. I'm glad you guys know better. Coffee. All right, everybody got their coffee, their fruit roll-ups. What is that, Hannah? Jerky, what is that?
Turkey bacon.
Turkey bacon. Oh, well done. Let's see. I don't see any reason we shouldn't share a screen and get going. So the beauty today is to introduce you. I got up early this morning and made a little bio for our good friend, our soon-to-be good friend, Leonhard Euler. Up to now, when you see the word E-U-L-E-R, you would have said Euler. But Euler was a genius. So let's start off with a little bit of Euler facts. I, of course, went to that great source of truth, Wikipedia, this morning and created this fine page for you to consider. It also happens coincidentally. I was just thinking Euler's method. Oh, that's right, Euler. He's a great guy. Let's talk about him for a minute. But as I was looking at this, I realized, wow, he's actually responsible. I kind of forgot he's responsible for actually a bunch of things we're going to do in this class. So as it says, his name is pronounced Euler. Born in 1707, and another mathematician, Pierre-Simon Laplace. I mentioned yesterday, coincidentally, that I'm going to show you a trick to solve differential equation later in this term called the Laplace transform, and this man's Pierre-Simon Laplace is responsible for that. And his comment on Euler was, read Euler, he is the master of all of us. So even his fellow famous mathematicians proclaimed him amazing. You may notice in this strange picture that his right eye is kind of weird. Later on in life, he went blind, and I'll mention some of that a little bit later. I'm not sure I understand the head wear, though. What is that, 300 years ago, almost 400 years ago? No, I'm lost. 320 years ago. I don't know how hats could change that much in 320 years, but just responsible for a ton of stuff. Not just a mathematician, a physicist, astronomer, geographer, logician, engineer, studied graph theory and complex analysis, and for us, infinitesimal calculus. And interestingly, just a few things like this, things you've taken for granted over time, but the notation of a mathematical function, in other words, f of x equals 2x plus 3, he's responsible for that. Genuinely, probably is the greatest mathematician in history, but certainly was one of them, and certainly was the most prolific mathematician of all time. 92 volumes of stuff he invented. Unbelievable person. So look at this list, though. This is pretty fascinating. He was the one that popularized the letter that we all consider pi. Taken off. Change your mind.
I'm just laughing about pi.
She changed her mind. She changed her mind.
He's trying to convince you that great mathematicians are of far great interest. And actually, having said that, I did read an entire book on pi. So I guess I can't
Nerd.
really, pretty much, it's all because of him.
Nerd. But this is kind of cool. Notice those of you that took 253 sigma, the Greek letter sigma, he's responsible for that kind of being used as a thing. And the letter I that we use for imaginary numbers, that's him, and f of x is him.
Did he kick off all of the Greek letters, starting to use those in math? Is he who kind of started it?
Yeah, it's a good question. I actually don't know the answer to that. I don't know if he kicked them all off, but maybe that was the genesis of that. I actually don't know. But if you took Calc 3, 253, this ubiquitous number E, the constant E, and that is Euler. The reason it's an E, Euler, is the reason. He's the one that, if you will, invented and popularized it. And he came up with this formula, which I showed you in Math 253, and we're going to make some use of in this class. Amazing. We'll tackle that later on. Couple of interesting, famous stories. 1927, I think he said he was born in, what was it, 1907. So the dude is 20. And he entered Paris's Academy Prize problem competition. And one of the reasons I love this is look at the competition. Best way to place the mast on a ship like that. Oh, that's near to my heart, not because I necessarily love ships and sailing, although I do like sailing, but just because it was a practical problem. You know, they're trying to figure out, where should we put it? You know, should it be too far forward, too far back? He came in second, it says, as a 20-year-old, but later on went on to win this prize 12 times. And he lost his vision like around age 59. But the reason that picture looks so weird of him up there, and lots of pictures show him, they called him the Cyclops, because one of his eyes was gone really early and he lost his vision kind of later on. Also has a penchant for hats. There's another weird one. But he remarked on the loss of his vision. Now I'll have fewer distractions. That's a positive attitude. We can learn from that.
Yeah, that's what I would say.
That's awesome.
That's funny.
But it's interesting because it says that condition appeared to have little effect on his productivity. Isn't that weird? Most of us would be like, I'm blind, I'm done. But it was said of him that he memorized the entire Aeneid, which is a book about yay thick, from beginning to end, and for every page in the edition, he could indicate which line was the first and which was the last. Like, how do you have a memory like that? I can't even comprehend that. But his productivity, it says, in many years actually increased, and he produced on average one paper every week in the year 1775. In other words, he came up with something new once a week. That's insane. Anyway, that's just kind of cool. I'll post this, but crazy dude. It's just weird I think it's just kind of neat to stop every now and again and think about. I've often said when I teach my math classes that, you know, all we're trying to do is just hike down a trail that leads to some beautiful waterfall. I like to think of math as, you know, going to a beautiful spot and just seeing what it is and so forth. But we're walking down a well-established trail with signs and maps and so forth. But, you know, if somebody had to be the first one to just wander randomly through the forest with no hope necessarily that there would be anything worth finding out there. I don't know if you've ever had the occasion of walking randomly through the forest, but you know, somebody had to be first.
I wonder if he was like contracted out by a king or something, because that was kind of often back then.
Yeah, the modern day equivalent is you're a PhD professor of math and you teach a class or two. You condescend from your ivory tower to teach some lowly undergrads, and then you're basically getting mostly paid to create new stuff effectively. But yeah, the original equivalent of that was a king or some rich person who would basically pay you to sit around and think, and then they would, you know, maybe some of it was benevolent on their part, but the other part of it was they got to kind of share in the glory of whatever their discoveries were.
Yeah.
So that's kind of cool if you think about it. But yeah, interesting dude. Anyway, maybe you should go hat shopping after class and become an Euler fan. At least now you don't have to worry about what you're going to dress as for next Halloween. All right. Euler is you. So what is Euler's method? And I mentioned in that little brief bio intro that he studied infinitesimals, which is initially what kind of calculus was described as is tiny stuff. And dy dx is a tiny amount of y and a tiny amount of x. And so they use the word infinitesimals, and Newton, I think, was the progenitor of that kind of concept. And so he studied that a bit, and that's kind of where this method ultimately came from. And so if you think about it, here's the principle behind Euler's method. Let's just keep it real. Okay. So let's consider the equation dy dx equals x plus y. Let's see. So when I was just talking, my screen went black. Did you guys notice that or not? You noticed it? You still hear me, but you don't see anything. Is that right?
There's like a couple black bars on your screen that we could see. One on the top and one on the right side.
No sense. It seems to happen every time. I don't get it. Anyway, whatever. So let's consider this differential equation, and let's kind of start out at the point, I don't know, the point 3, 2. And so you would say from yesterday, hey, we could make a direction field for this, or a slope field. And so if we went to the point 3, 2, then you of course would say, let's see, let's make this a little more interesting so it comes out a little better. Let's make it x minus y. So then you would say, okay, cool. If you start at 3, 2, then the slope would actually be 3 minus 2, which is 1. And so then you would say, okay, cool. The slope right there is 1, and you'd sort of draw a little slope. But you understand that doesn't continue very long. Does that make sense? So Euler's method, and this is exactly why, as I showed you yesterday, why one of the names for the method here was actually called Euler. I mean, maybe you remember that from yesterday. I showed you kind of the different methods by which these paths through the slope field are paths. And so we're going to do that today. And I mentioned that we would. So the idea is, okay, well, hey, there's that little slope right there. Well, now that you're armed with a point in the slope, does it make sense you could find the equation of that little line, which is how those little lines were made? So you'd say, oh yeah, I know how to do that. Y equals mx plus b is the equation of a line, and I know that the slope is 1. And if I go plug in the point that I'm at, when x is 3 and y is 2, then that'd be, let's see, 2 minus 3 is, b would be -1. And so you would say, ding, ding, the equation is y equals x minus 1. Does that look about right, by the way? Just thinking, does it look like that would cross down there at -1? The y-intercept of -1 kind of does, kind of looks like it, doesn't it? So then the idea was, okay, well, now that we actually know that little line, and as I said, that's how a direction field is made. You got to know the equation of the line, and then you just have to graph a little tiny chunk of it, like you would sort of graph that, if you will, from x is, let's see, if it was at 3, then it'd be like 2.9 to 3.1. Does that make sense? Like that's all I'd want, is a little tiny chunk of it. But the idea of Newton's method is super simple, and I always want to, take time to explain how easy things are anytime I can. Before we sort of proceed to the quicker, I mean, you'll read this section in the book, and this is a good example. And I for those of you that, I don't know, studied enough math, I find myself reading the textbook. I find myself not making much sense of it when I first read it, because it's a little intimidating. Like I look at the pages and I just think, wow, this is symbols everywhere and so forth. But
of course,
it's not hard. It can be understood. I only have a bachelor's of mathematics, not a master's of math. My master's is in education. But it can be understood more simply all the way through. Like everything I've studied can be understood simply. And I'm going to illustrate that right now. And then we'll go back and talk about the complexity of it and so forth. The book's not wrong, by the way. It's just that it proceeds to a very cool abstraction, and then it explains it in language that's oftentimes kind of hard to make sense of unless you've really had a deep grasp of all of the terminology that's associated with this.
Well, the notation makes it look a little scary too. Like
Yeah.
like two equations that are really simple, but they're not. They don't look nice.
Yeah.
They've got subscripts, which is always scary.
Yeah, very well said. Like the subscripts are very intimidating here if you don't make sense of them. And so again, I want to show you this just a lot more simply than that. So the idea then is we say, okay, cool, I'm right here. But does it make sense that's not where we're going to stay? Because this is going to go off and curve around and do something super fun, right? We saw that yesterday. The solution to this will be some equation that's really interesting and kind of have some hoop-de-doo to it. So the idea is, could I proceed along that line just a little bit? Could I just cruise along that line a little bit? Now, I don't want to go very far, right? Because we know this thing is actually curving. And so I don't want to follow that clear out to here. I don't want to follow it very far at all. And so let's just, for the sake of argument, let's let x, let's increase x by 0.1. And so in other words, x was 3. So we'll say x of 0 to help you introduce these subscripts. We'll say x started out at 3, and then our first step, we're going to take it up to 3.1. And so where are we now? Does this make sense? We're at a new point. So I started out with 3.2. Where did I get 3.2? Just pulled out of the air. And so let's go to 3.2. Let's make a graph from there. So now if I go to 3.1, does it make sense I could put 3.1 in here for x to see what y is that goes with it? That's the value of that equation. So if I do that, of course, I get y is 2.1. 3.1 minus 1, 2.1. So I sort of have my ordered pairs. I started with 3.2, and I just got to 3.1, 2.1. That's like my second ordered pair. And now I just start over.
So our second position is where we land. then.
Yeah.
Okay.
So we just landed at a new point, 3.1, 2.1. Now we start over. So let's make a list here. So our slope started out to be 1. And notice in this case, it's kind of interesting because the slope formula says x minus y. Notice if I go x minus y, I get 1 again. So the slope didn't change very much right there. Well, it didn't change at all. So then I make a new equation. Let's go back and kind of even list this out. My first equation was y equals x minus 1. My second equation then will be y equals 1x again. And oddly, I think it'll be the same exact equation. So that doesn't usually happen. But notice if I put 3.1 in there, 3.1 minus 1 is 2.1. So that equation still works. In other words, I took a pretty small step. I hope I didn't accidentally start on a line or something stupid. I might have started at a weird point. Remember yesterday how some of the curves were actually straight lines? Maybe I got unlucky here and started on a straight line. That'd be unfortunate.
Some asymptote.
Yeah, like that kind of asymptote that David mentioned yesterday. That'd be very disappointing if that happened, but it's unlikely. So let's proceed. So then I say, okay, cool. So now I have this new point. And now what am I going to do? Well, again, I'm going to increase. This is really important right here. What's my increase? I'm going to call this for the rest of the day H for that little step. This is kind of our step. In other words, how far are we going to move along? So I'm going to step 0.1 further. So that means my x just got up to 3.2. And then I'm going to put 3.2 into this equation right here. 3.2 minus 1 is 2.2. Geez. Wait, am I going to get the same exact thing again? Wow. This is terribly unfortunate. It's acting, is it going to stay this way? Let's cheat for just 1 second. Since this is good for us. Let's go find out if I'm the unluckiest person on the earth. Let's see, yesterday where is that? So I'm click. So I'm opening up the GeoGebra version of the slope field. Let's see if I got unlucky. This is very annoying. Why does it do that?
You gotta push enter after. Yeah, and I push enter. There you go.
Did get unlucky. Do you see that?
Wow, yeah. Right on that
Then I got
line.
unlucky.
Hilarious.
That sucks.
So that's good. That's
You
good
could use the
experience. Though.
You could use the same graph and just start at like 0, 3 or something.
Yeah,
See what-
start at a new point. That's exactly right. So I'm gonna just since we're here anyway, let's go. That looks kind of like a fun point. 1, 2. So if I start at 1, 2, it should kind of go down and then cruise back up. So the idea here is how did GeoGebra do this? Well, it used Euler's method. So let's go to 1, 2 and kind of redo this.
with a gazillion steps.
Yeah, with a ton of steps. So, all right. So that's okay. It'll give you time to kind of soak on it for a second. Okay, so we decided to go to the point 1, 2. We said there was a slope right there. We started at the point 1, 2. It shouldn't take us too long. So dy dx then would be 1 minus 2, which would be -1. So our first slope was actually -1.
Oh, your screen went black again.
Yeah, I see that. Man, I wish I understood what was causing that. It's not a power issue, and it always seems to stay gone for the same amount of time. Like 10 seconds or so. Maybe I should just get rid of the other screen since I'm not really using it. Now I see I'm frozen. So I'm going to do this kind of fast, so help me correct if I get this wrong. So I found the slope was -1. I'm looking at this right here, and then I plugged in 1. So we end up with b being equal to 2 plus 1. When I add that 1 to the other side, so b is actually 3. So then I say my equation is y equals -x. Probably going to make a mistake. I'm going kind of fast here. -x plus 3. Let's stop and make sense of that. Does that make sense? The answer is no, because the slope wouldn't be negative. Oh, yes, I guess it would. I just assumed it would be positive.
Yeah, it would be negative there because it dips and then it like shoots up.
Yeah, we saw that graph dipped a second ago. And so if the slope
Right.
was -1, then the fact that it intercepts up there at 3 would make sense. And so I think we're okay now. So then my equation is -x plus 3. So then I go take my step, my 0.1 step. So let's rebuild all of this. So my slope was -1. My original ordered pair was 1, 2. I take my 0.1 step for x and let x grow to 1.1. And then I put 1.1 into this equation here. -1.1 minus 3 would be -1.9, positive 1.9. Again, tell me if I do something stupid here. And now that I have established myself at a new point, and that's the key thing I want you to understand is we started out at this point here. We found the equation of that line. We took our little miniature step, and now we just reestablished ourselves at the point 1.1, 1.9. I'm getting a new monitor today. Maybe it's the cheesy monitor that I bought at Best Buy. I don't know. So you guys can hear me now?
Yep.
Yeah, I can't see you though.
Screen's black.
Okay.
Oh, I mean like
Yeah,
striped.
you see nothing, right?
Yeah, some kind of loading thing.
Any computer studs in here? What would that happen? It's a brand new laptop.
It might be because of like inactivity. It could be going into kind of a standby mode.
I was wondering.
I could probably
also
show you how to turn
switching.
that off later.
You're switching back and forth between what you're sharing, and that might get a little confusing. Like when I tutor, I sometimes share my screen from my iPad, and I don't know. I don't know what happens. I don't know anything about computers, but it is weird sometimes. So
Yeah, it kind of behaves wonky. I don't know. So
there's quite a bit of lag when I do it.
yeah, some lag time. So now that I went to a new point, I'm at the point 1.1, 1.9. Does it make sense I could go back up here to my slope and recalculate my new slope? And of course, my slope should change. And so maybe it's good that we just saw that, well, not necessarily. 1.1 minus 1.9 would be -0.8. Tell me something about that you're not surprised about. Why are you not surprised? Kind of asking you to read my mind here a little bit.
The slope's not quite as steep as before.
Yeah, it's not quite as, it hasn't changed very much. It's not quite as steep. Notice it's kind of leveling off. Well, based on the cheat that we just did a second ago, no wonder, right? We actually saw that it's going to kind of curve and do this, right? So it's actually leveling out a little bit. But the fact that the slope before was -1, this isn't going to come out and be something like if you do this and you get 7, that's not happening. Like it's going to be something really close to -1. Why? Because we took a tiny step, so it hasn't changed that much. So the fact that we got -0.8 really isn't all that surprising. If I'd got -1.1 or -1.2, I wouldn't have been surprised by it either. But the point is I'm going to get something kind of close to that. So what do? Then I just repeat the process. And again, I'm doing this slow motion right now. We'll do this faster in a minute. But I say, okay, well, cool. I've got a new slope now, -0.8. And so I'll just kind of quickly do this. Then, of course, and I guess I'll write this here. Then I plug in the point that I'm at, x is 1.1. And I actually want you to think about this. I'll slow down a little bit. What do I do to find my b value? Think about this carefully. What do I do to find my b value now that I'd like to put over here?
You have to plug in the x and y of your new point in order to.
I plug that in, and because b is sitting here, does it make sense b will be equal to, well, 1.9, and I'd have to subtract that slope to the other side? In this case, I'd be adding it. I'd have to add 0.8 times 1.1. Like that's how I'm going to get my b value. So on my calculator right now, I'm typing 1.9 plus 0.8 times 1.1. And I get 2.78. What's not surprising about that? Again, I'm always trying to teach people to think. What's not surprising about that y-intercept?
It hasn't changed much either.
Hasn't changed much either. Also, if the slope is actually lower right there, wouldn't it hit lower? So not only is it not changed much, but of course it's a little less than 3. Isn't that kind of cool to think about? So I've established myself at a new location. And now I'm going to start over yet again. I'm going to say, okay, now let's take another step. I know you can't see this yet, but I guess it's coming back in a minute. Now I'm going to take another step, another 0.1. So my 1.1 grows to 1.2. And then I put my 1.2 into the equation, into the previous equation. I guess I'll erase this. Then I'm going to put 1.2 into this equation to see what my new y value is. So negative 0.8 times 1.2 plus 2.78. And I get 1.82. Again, I'm not surprised to see that that has gotten a little lower. It got a little lower. And now I have the ability to find a new slope. I go 1.2 minus 1.82 and I get negative 0.62. So notice the slope is continuing to kind of level off, if you will. And I repeat the process yet again with my brand new slope of 0.62. I'm going to quickly just calc this next one. I'm typing in x is 1 or y is 1.82. Plus, if I add 0.62 times x to the other side, x is 1.2, I get a y value of or a b value of 2.564. So do you see the concept behind Euler's method? It's kind of brilliant. It's kind of simple, isn't it? We're just creeping along this super simple graph. And so if I take really tiny steps like 0.1, and we're gonna do this differently than in the book because I'm gonna take some time today to teach you a little bit of thinking and programming and technology, because there's no reason we shouldn't be using technology to do this in a way better way. But let's talk about speeding this process up. In other words, and I want you to think about this right now and see if you can figure some of this out yourself. So my next x value, of course, will be 1.3. But if we were in a hurry, does it make sense we really don't need this entire equation? We don't need the equation. We just need this next y value right here. What are you actually doing by way of shortcut? What are you actually doing to kind of the previous location to get you here? That's what I want. That's what's in the book ultimately. And it just looks mysterious because they didn't slow down and explain it. What are you actually doing to get that? Well, let's think about what we did a minute ago. Didn't we have this equation up here? And effectively we took the x of 1.2 and we put 1.2 in there. And that's actually what spit that y value out, isn't it?
So you're taking your starting, well, you have your starting x and y value, and then you take your you take a step, or wait, to find, you're asking for the what, how do you get that next y value? So I think you would take
Actually,
the previous y value and add it to the step incremented, like to an incremented step of the f of x, y, so that you're I'm not explaining it very well. It makes sense in my head.
Yeah, no, I get it. And I'm glad you said that because that's what makes books hard right there. Something makes sense to you. How do you say it to somebody else that makes sense to them? Effectively, what we did here is we said, okay, let's take our step. We took our step and got us up to 1.3. And wasn't it actually, contrary to what I just said, wasn't it 1.3 that we plugged in there that would give us our next y value? Isn't that right? I take the line that I just established from the previous location. And so what did I really do? Well, didn't I take the slope? Let's think about this. I took the slope times kind of the next x, right? This was the previous x. This right here was the previous x. So I took the slope times the next x, but then I added it to, well, this b value, right? But where did that b value come from? How did I get that? Because remember, I actually don't need the b value. I really need the next y value. I don't really need the equation. So can we speed this up? Wasn't that b value? Let's see, what was it? It was found, well, a second ago, we took the y value. Let's see, the y value was 1.82. Let's go back and think about this. It used to be y equals negative 0.62x plus b, right? And we said, what is that b value? And so to get it, didn't we take this and move it to the other side? So we took our y value, which was 1.82, and we said that would be equal to, I'd have to subtract this slope multiplied by our x value to the other side. Isn't that how we got the b?
Right. That's our previous. Those are our two previous values.
Correct. But that's what we did to get that 2.564, right? Which is what we need now. So that means I basically added to it not the next y, but the previous y. And then I subtracted the slope times the x value. Isn't that what I did? Now, here's where math terminology might help us a little bit. So this was, let's do this. So we'll say this was our 0th term. That's in physics when you say t0, that means your initial time, your starting time. So that was our initial point, and this is our first point. So that would make this.
I
right
can see
here.
a big old sigma coming in.
That would make this x1 and this y1, and that would make this x2 and y2. Does that make sense? And that makes this x3. Tracking with that, okay? So what we're after here is basically y3. How do we get y3? So let's go try to rewrite what I wrote in words right here. Let's go try to rewrite that in this language. So I took my slope, which is, I guess you would say, is my m2 slope. This is my m0 slope and my m1 slope. My start slope, my first slope, and my second slope. So I took, just repeating this, my m2 slope multiplied by the next x, which is actually x3, right? Plus previous y, so that's y2, minus our slope, which was our m2 slope, times our previous x.
And this would give us the next y value, the y for the 3.
And wait, shouldn't that be x2 at the end?
Did I screw that up? Yes, I did. Thank you. that's 2. I knew something was wrong there. Do you agree with that? This is how you get your next y value. This is the key right here. Isn't that what, like, if you just want to skip the line, because we never needed the line, right? We needed the line to get our next y value. But did we actually have to stop and write the line down? The answer is no, you don't have to. Now, you might find yourself being a person saying, I'd rather write it down. Like I can make total sense of that. It makes sense to me. I don't like formulas and shortcuts. Now let's just stare at this for a second and improve it a little bit. Okay, well, notice there's an M2 here and here, which means I could actually factor M2 out, and that would leave X3 minus X2. Are you okay with that? I'm just put these two terms together. You okay with that? Please either ask questions or say, give me a second.
That looks good.
And then I just add Y2 to it. So I don't know about you, but I find myself thinking, does that work? But I want you to think about something for a second. What's this right here?
Right. That's
What
that's the step size.
That's
like
exactly
step.
right. That's the
Okay.
step, which for us was 0.1, or as I've been calling it, H.
Right. It's the
So-
difference between the two x's.
Exactly. It's the difference between the two X's, which is always
And
the
then-
step. And so effectively, this
and
is
then
what you'll
slope
see.
is-
This is what you'll see in the book. And so this is the shortcut. This is the shortcut because all we really need is this. Do you agree with that? I don't really need to write down the slopes. I don't need to know the slopes. I just need to know the points. Isn't that all it takes to make a graph? So how do you get them? This is then what you see in a textbook. They would say, if you want the next X value, then take the previous X value. Does that language make sense? If I say X of N and then N plus 1, then that'd be how you go from X2 to X3 or X4 to X5. Which is kind of cool. I mean, that's a great way to say it. And you just add your step to it. Whatever your step is. So we started at X is 1, and then we went to 1.1, and then we went to 1.2 by adding our step to it. How do you get your next Y value?
You take your previous y value
Take your previous Y value.
and you add that to the step size times the slope of a value of the previous position.
Yeah, of the previous slope. So that would be the slope, the same place the Y term was. If we're at the previous value, if this was Y2, then that'd be the slope, M2.
And that would just be the derivative. That would be the differential equation evaluated at the previous point.
Exactly. And so you in the book, you would see something more complicated for this. They would say, and they're not wrong, they would say that slope is what you get. In other words, it's kind of evaluated at the previous two values. In other words, you plug in your previous two values to get that slope. Now, all I would like to do is let's do the same thing. Let's not make this chart this time. Let's just do this to the same exact problem. And so we say that our dy dx, or since I'm using m here, our m slope is found by just going x minus y, right? And so we chose to start out at our ordered pair 1, 2. And I guess we need to write down our slope as well. And so we plug our slope in there, 1 minus 2, we get a slope of -1. So how do we get when we move to our next point, how do we get our x? Well, we take, according to this description up here, we just take our x, our previous x of 1, and we add whatever our step is to it. So there's our next x. How do we get our next y? Well, see, this formula says, what do? We take our previous y, 2, I'm looking at this right here, previous y, We add 2 at our step, just multiplied by the slope, previous slope. So we add 2 times our step, which was 0.1, times our previous slope, which we already had was -1. -1 times 0.1 is -0.1. 2 plus -0.1 is 1.9. Hey, that's working, isn't it? Isn't that what we got before? Cool. Then what do? We say, okay, we're not done. Well, let's find some more points. So what do? We increase our x. Then what do we do to find our next value? We take our previous y value of 1.9. We add it to 0.1 multiplied by our slope. What's our slope? Uh-oh, I never figured it out yet. I got to go back and figure that out. I take 1.1 minus 1.9. I get -0.8. So I take 1.9 plus 0.1 times -0.8. And I get 1.82. Let's do it one more time. Now I go to my next point, 1.3. Let's find our slope since I realize I need it. I go, in this case, x minus y, 1.2 minus 1.82, I get -0.62. How do I get next y value? Take my previous y value, 1.82. I add it to the step multiplied by our previous slope, 1.82 plus 0.1 times -0.62. I get 1.78758. So do you see how I never, this is what I needed. I needed these ordered pairs so that I could make a graph of this thing. I never needed the entire equation. Is it okay to write all that down and go to that trouble? Sure, but you don't really need to. I also would like you to think about something else that's really logical. This part of the term right here, I think I'll erase this. No, I don't. I will. Let's think about what that actually is right there. Isn't this h a tiny amount of x? That's what that is. By definition, our x is our step, and we're going to make that small. So it's a tiny value of x. What's slope? Isn't it a tiny change in y divided by a tiny change of x? What happens when I multiply those?
Units check out.
These babies cancel, and I get a tiny change of y. Oh, well, let's think about what that makes. Doesn't that make all kinds of sense? What did we do up here? We took our original x and we added a tiny amount of x. What do we do with y? We take y and we add a tiny amount of y. Isn't that kind of cool? They're not the same. The tiny change of x is always 0.1. The tiny change of y is not always 0.1. Notice the change right here went from 2 to 1.9. So that was -0.1. And then it went -0.08. And then it went, who knows what that is, 0.7, something like that, 0.6. So that actually makes sense if you think about it. We're black again. I'm obviously going to have to get to the bottom of that. Are we back yet? So come on. So I think you can still hear me anyway. Let's do this with the equation x plus the sine of x. That'll be our derivative equation. And I'm making that up, so I don't know if this is going to be cool or weird. going on?
Well, if Euler's coming up with all these blind, I have the same level of respect for him as I do for Stephen Hawking.
No kidding.
Mhm.
Let's see, I hear you guys now.
Do you want x plus the sine of x or the sine of y?
Oh, that's a good question. Yeah, let's get y involved. Let's do y plus the sine of x. How about that? We do need to get y involved. So our dy dx will be y plus the sine of x. And let's start at the point 3, 2.
We can't see that, by the
Yeah.
way.
You know, keep hoping it'll just show back up again, but trying to give you at least enough to start. So the dy dx is the slope equation is y plus the sine of x, and we're going to start at the point 3, 2. So what I want you to do, and let's choose a different step size this time, just so that you're thinking. Let's see. Let's make it 0.2 just to do something different. Let's make the step size this time 0.2, just so you're having to notice there's a difference here. Come on, machine, wake up. What's going on? Definition of insanity, keep doing the same thing and hope it does something different.
There we go.
Who knows, but now we see something. So make sure you're in radian mode. I see that I'm in degree mode. So my first slope, I'm going to take y, which is 2 plus, I'll say here also h. We said where h is going to be 0.2. So I take y, which is 2, plus the sine of x, which is 3, and I get 2.14 for my slope. And rounding is an issue here, but who cares? Let's not worry about it. I'm going to round to a couple decimal places. So awesome, I'm done. I established my first little tiny line, if you will, at the point 3, 2. It's a slope of 2. And so let's proceed. So then we say, okay, well, let's find the next term. Well, I let my x increase. So this time it was 0.2. Now, how do I find my y? Let's see, what was the formula for that again? I take my previous y, which is 2, and I add to it our step, which is 0.2, times our slope, which is 2.14. That's what it was. And I get 2.428, 2.43. Again, it would be better. I use 2.14 for my slope. I'd be better if I left it accurate, left it exact, but I just use 2.14. And now I'm in a position to go get my next slope, right? So I can say my next slope is y plus the sine of x. So y is 2.43 plus the sine of 3.2. I got 2.37. Notice again, things aren't changing a ton. We saw y went from 2 to 2.43. We saw our slope was 2.14 and it just got a little steeper. So our point moved up and it got a little bit steeper. Now,
How are you calculating the slope?
what's that?
How are you calculating the slope?
Putting it back into this equation. So I put 3.2 and 2.43 into that equation to get that slope.
Gotcha.
Thank you for asking. Now I proceed and say, okay, let's keep going. Because remember, I'm trying to draw a graph and I've got 2 ordered pairs now. I just need a bunch of ordered pairs. So
Wait,
go ahead.
question.
Yep.
So when we so if we wanted to calculate y sub n as y sub 2, right? We would take our our previous y value and add that to h times the slope, which is evaluated at x sub 1 and y sub 1.
That's right. In other words, I got this right here by taking the previous y and adding to it our step, which was 0.2, multiplied by our slope, which was 2.14, previous slope. That's how I got that 2.43.
Right. So I'm just clarifying that what we plug into the differential equation for the next value is the value that we're on. So if we wanted to do it, I'll just let you do it for 2 and then I'll.
Got it. Yeah, so it is kind of important to kind of have that written down, which I'll quickly rewrite
Right.
here.
I just want to make sure what I have written down isn't wrong.
Yeah. Our next y value is found by taking our previous y value and adding our step multiplied by our previous slope. That's one way you could write this down. So now that I have that x, I can get my next y by taking my previous y, 2.43, and adding it to the step, which is 0.2, times my previous slope, which is 2.37. So 2.43 plus 0.2 times 2.37, I got 2.904. I'll call it just 2.9. And now that I have that, I can go back to my equation for slope, now that I have an x and y, and I can establish my new slope. Notice my slope is changing. That's kind of good because that means I land on one of those lines, one of those asymptotes, if you will. So if I take y, which is 2.9, and I add that to the sine of x, which is 3.4, I get my new and improved slope of 2.64. So notice my slope is still increasing. Let's do one more, and then we're going to jump to Excel and technology to take care of this stuff for us. So I let my x increase by whatever my step was. I find my next y value by taking my previous y value of 2.9 and adding to it my step times my previous slope of 2.64. So 2.9 plus my step of 0.2 multiplied by 2.64, I get a brand new y value of 3.428 or 3.43. And so what am I doing? Well, I might want to sort of say, this is kind of what your assignment would be. We'll say kind of like dot, dot, dot. How about if you keep going until your x value makes it to say 5? And really that's the question, like what happens when you get to 5? Because remember, we're doing this by hand. Remember, Euler was doing this not only by hand, but was without a calculator, let alone anything good to write with. It wasn't like a quill, a bird feather with ink in it back in that era, and blind with an ink feather. Ridiculous. I don't understand that. Okay. Now, and I actually want you to do this with your assignment. You see Excel now, and I want to do exactly the same thing, except we want to let Excel do the work. And so this will be my n, this will be my x, this will be my y, this will be my slope. And I chose to, here's a couple of tricks. Please interrupt and ask me about this if you've never seen this before. But if you grab, I'm kind of a freak for symmetry, so those are centered. If you grab those first two numbers, 0, 1, it kind of understands, oh, you went from 0 to 1. And then if you grab that little black or that little box in the corner and drag it down, it kind of understands, oh, I see what you're doing. You're going from 0 to 1, so your next term would be 2. So I can kind of drag that down and kind of get the first 15 terms. And we said our first x was going to be 3 and our first y was 2. And then what do we do to get our slope? In this case, did we not? And this is the language of Excel. We took the sine of 2, we took 2 plus the sine of 3. So in my case, I'm going to say equals this cell, this slope will equal, this is the language of Excel if you've never seen it. This cell is going to equal this cell plus the sine of this cell. Isn't that the slope we got a minute ago? Again, please interrupt because I actually want you to do this. I'm going to give you a different assignment today. I'm going to give you tiny steps instead of 0.2 and 0.1, which is what you'd have to do if you're going to do this by hand. We're going to have tiny steps like 0.01. Let me show you that again. So that's my slope formula. Now, here's where it gets really cool. My step, I think I'm going to go up here and put it in this box. My step was 0.2, right? So then how do I get the next value here? Well, I could just do it in my head and say this cell will be 3.2, or I could say this cell will be equal to this cell plus this cell. Oops. Why did I do that? Some of you computer people, why did I do it that way instead of just typing 3.2? Because I totally could have done that.
So you could drag it down and it'll.
Yeah, so I
fill
can
the
drag
other
it down.
boxes.
And then also I could go up here and say, what if I want that to be 0.1? And you see I don't have to start over again.
You're assigning a variable.
Watch this though. If I drag it down, it doesn't work. Anybody know why? Take a look at the formula. That says take C5, yeah, that's 3.2, but then add it to D3. Notice D3 moved down too, like it's trying to add Y to it. Who knows how to fix that in Excel? You put,
Yeah.
go ahead.
Absolute cell reference with F4 on your step value.
Yeah, you go to the previous formula and you want what's called an absolute cell reference.
I think your audio went out.
There, is it okay now? Oh, I
Yeah.
gotta hit shift. So if you hit F4, then it'll put $sign in front of D and $sign in front of 2. And then when you drag it down, that's an absolute cell reference, meaning, hey, I don't want you to move down. So now I can drag this down and I have all the X's, 3.2 to 3.4, 3.4 to 3.6, 3.84, and so forth. Now, what do I do to get the next Y value? Didn't we take the previous Y value plus the step times the previous slope? So
Yep.
this cell will equal the previous Y value plus the step, which I would like to be absolute referenced, and then times the slope. Wasn't that our next? I hope it wasn't looking right now. Wasn't that our next Y value? Yeah, it was 2.43. So 2.4282. Yep. That's how we got our next Y value. How do we get our next slope? Well, isn't this what we did? This says the formula was D4, which was this cell, the 2 plus the sign of this cell. Well, all I gotta do is drag that down. Does that make sense? So our next slope was 2.37. Yep, I'm sorry, yeah, 2.37. So there it is, 2.369. And so now I'm in a good place. Why am I in a good place? Because all I got to do is just grab these and drag them down. There's my next answers. So when we got to 3.4, actually that isn't right. So
Yeah, those numbers are right.
yeah, they are right. Good. Those numbers look right. And then if I drag it down one more time, yeah, those numbers look right. I never got around to finding the last slope. But does it make sense now that if I drag this down, I don't have to do the work anymore? This is what computers are good for. Now here's what's really cool. If I grab all of these numbers right here, just my X's and Y's, and I go up here to insert at the top, insert, and this one right here is a scatter plot of those. There's my graph. That's what those cheap programs that we found online were effectively doing. In other words, you could write this for yourself. Now notice that only went forward. In other words, it went from 3 to 3.2 to 3.4. Could I also get it to go backwards too? You know, like get the graph going the other direction too? Yeah, I'd have to think about that for a second. I want to get it, but without erasing what I previously had.
Yeah, if you made it negative, you could go backwards, but then you wouldn't have what you already made.
Let's just do that really quick. Can I just literally change that and it goes backwards automatically? Yeah, it does. But I just lost what I already made. So could I just copy all of that? Could I just copy all of that? Then I got to get them all to appear on the same graph.
I don't think your copied your like cell references and stuff.
Yeah, it didn't.
You can keep the copy as negative 0.2 and then reset your other one to 0.2 and it should work.
What's your idea? Why didn't that work?
So it copied the numbers, but if you look at the cells, it just copied.
I copied the.
For some reason,
23.
your 3 just isn't going to 3.2. It's still going negative.
So I think it's still referencing D3.
Yeah, it's still referencing the wrong cell, so it's got to reference D21.
Yeah.
How's that working now? Let's see, did I use that anyplace else? D21. Is this working now? I think that's working now. Anyway, I don't think I'll play with that anymore, but do you see the concept about kind of where this is going?
Yep.
And how, you know, how, if you will, this is working. And you can appreciate, maybe now you understand, why did the graph go off the rails when it went vertical? Well, what's going to happen if you get a slope that's infinite? What's it going to put right here for slope? It's going to say undefined or something like that. And that's where it's going to break. Does that make sense?
It's cool
So-
that the differential equation contains enough information to do this much.
Isn't it weird? Isn't it? It's kind of crazy.
Well, it just makes sense why we had all those chapters in like differential calculus with like information you could extrapolate just from the equation.
Powerful. So I want to play with this just for a second because I'm a curious human being. Let's see, I'm in G21 now. So I'm going to change this to look at G21. I'm only doing this for the fun of it. So we started at the point 3, 2. This isn't what I want to do. No, I'm wasting time. I'm not going to do it. So this is kind of powerful. Well, actually, this is kind of what I want you to do for your homework assignment. So let's just build one more from scratch, except for let's do this on another level. So H. I'm going to make H really tiny this time. And this is why you would do this on a computer, because now we're going to make really tiny steps. And just so that it's written down, let's say our slope, what shall we make it? X squared minus the cosine of 2y. How about that? That'll be our slope formula. Again, I'm making this up, so I hope this comes out fun, but maybe it won't. I don't really need the n, do I? So I'm just going to have an x and a y and an m. I'm going to give you a second to try this yourself first. If you have Excel open and you're playing around with this, I'd ultimately, because I want an Excel level answer for your 2 homework assignments today. So let's try starting at someplace negative. Again, this is dangerous because I don't even know if this will work, but let's start at x is -2. I want to give you a second and see if you can kind of write this yourself. Just give you a second to think about it. By the way, see that 2y up there? Excel doesn't like that. It's gonna want us to say 2 times y. It's sort of not an algebra program. So my slope here will be x squared. So I'll say equals this cell squared. And I am subtracting the cosine of 2 times. Notice that's kind of covered up. So that's C6 that I'm at. So I'm just going to type it, C6. So I got a pretty steep slope there. So then my x is going to be increased or decreased by 0.01. So I'm going to say this cell will equal this cell plus my step. And I'm going to say function F4. So yeah, that did increase by 0.01. So now I have, a bunch of those. Look, it's working. They're going up by 0.01 every time. Okay, great. Except for this time, I want to go a long ways. Let's go all the way up to 1. I'm going to work my way from x is -1 all the way up to x is 1. And I'm taking a really tiny step this time. So what's my next y value? Well, my next y value equals the previous y value plus our step, which again, we want to be permanent. So I'm going to say F4 times our previous slope, which is right there. So there's my next y value. What am I not surprised at? Well, it didn't change very much. It went from 1 to 1.04. And our slope was found by just taking these 2 terms and sticking them into that formula. So I don't have to do anything there, but just add that down. So let's see, is this working? First of all, notice the slope got a little bigger. Not much, but a little bit bigger. So let's take one more step. If I just drag both of those down, notice my y value got a little bit bigger. My slope got a little bit bigger. I wonder if the slope's just going to keep getting bigger, 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 or hopefully it'll get bigger and then it'll get smaller just because that's kind of fun. It'll make a fun graph. But again, I'm purposely making this up from scratch just to see how it'll behave. So now I'm going to drag this all the way down, and I just did, I guess that would be 200 steps. Can you follow that? I went from x is -1 to x is +1. Oh, good. The slope actually got smaller. Isn't that fun? So I just did 200 steps of this. So I certainly don't want to do that by hand. So now that the fun part of this is, let's grab the x's and y's and make a graph of it and see what it looked like. Please interrupt as usual. Actually, one thing I don't know how to do that I can't remember is how to just go to the top a lot faster. So I grabbed all those, I go up to insert, I click on charts, and I go to scatter plot. Oh, that's a fun one. That was a good choice. We got lucky. Notice there's 200 points there, and they're so close together you can't even tell they're points. They're touching each other. Is that cool or what?
Nice.
Nice. So actually we started at x is -2. So we went from -2 to x is 1. That's actually 300 points. So we just did 300 steps of 0.01. So notice our graph is going to be ridiculously accurate because our step was so small, right? Now, for the fun of it, let's go back here and cheat and do it using the So how come it's not the same graph? That's a duh. I'm asking kind of a dumb question, but why isn't it the same graph?
It's at 1, 2. You got to move it.
Yeah, got to move it. We started over here at -2, 1. So is that the graph we saw? Sure enough.
Yep.
Isn't that cool? So again, we got kind of lucky because this was a pretty fun graph. So let's go find another point over here. Let's go find another place where the graph is really interesting. So let's see, it goes down. That's kind of fun. It's got a little hoop-de-doo in it. Let's see, I got to get to a spot that's a little nicer. There we go, 0, -1. So what if we started at 0, -1? How much do I have to change about this formula over here to do this?
Probably just the first x and y.
I think just the first x and y. Same? At a glance, I'm thinking no.
I think it is. You got to zoom in a certain way.
Yeah, the scale is really weird. I think is the kind of cool. Man, that's a crazy graph. That's a fun one. So can you see how this works now? Like, can you see why there are GeoGebra softwares that kind of do this automatically? It's actually not that much of a jump from these two examples. So
I see it.
pretty awesome. So with respect to your assignment, I guess I'll go back and talk about that in a second, and then we'll see what you want to do after that. And I think what I copied for you out of the book here, if you don't have the 8th edition, says this. but just so that I write it down someplace so that we're all looking at it. What's going on here? Share. Here we go. I've also noticed my screen seems to go black like at the start of the day and it doesn't toward the end. Probably jinxed it, but. So for your assignment, I don't want you to follow the directions. You're doing questions 6 and 8, but I want you to use the step, or what I've been calling H, to be 0.01, not what they said in the book. Secondly, for question 6, I want you to find y of 2. In other words, x is 2, find y. I think it starts at 1, like x is 1, starts at x is 1, and you're just going to, so you have 100 steps to make. Well, you need to use Excel to take 100 steps. For question 8, I want you to find x of 3, and that's kind of confusing that it says x of 3, but that's because I think they used x's and t's for the letters. Now, you may have never seen Excel before in your life. So that's a pretty tall ask if that's you. Ask me questions. Did I go too fast there? Would it be, I'm trying to decide as a teacher, should I just post that Excel that I made so that you can kind of steal off of it? My gut reaction is yeah, because this isn't an Excel class.
I think that'd be cool. I haven't used Excel. I can't remember the last time I used it, but it didn't look that hard to be able to type it in, but it would be nice to have the reference.
Let's do it. It's kind of neat to know. I guess that's what it comes down to. That's why I'm showing this to you. It's neat to know. And of course, ultimately, we're not going to be satisfied with this. We actually want the equation. We actually want to be able to solve the differential equation, not just kind of get a look at its specific graph. So I want to do one other thing with you just because we have time and because it's kind of cool. We got kind of lucky on that one. Let's see, do I want to risk it again? Let's do a slightly simpler equation. Let's do one last example, but this time I'm going to write a TI program, because again, I think this is, you don't need to do this. You don't need to know this for this class and so forth. This is kind of a hard thing for me to put on a test, and we'll see when we get there. But I actually want to write an iterative program for you, and I am not a programmer. So everybody's going to be able to understand this. It's just kind of neat to see. Let's do it for this. Let's make dy dx. Let's keep it kind of simple. Let's see. Let's try something a little bit. No sines and cosines. Let's go x cubed minus 4y. So again, we can cheat. And actually, let's do that first. Let's go x cubed minus 4y. Let's go see if that's an interesting graph before we do this. I think it's kind of fun to make stuff up on the fly for your sakes. So that's kind of a fun one right there. So let's what I'm trying to do is find a cool place to start. So let's start at -3, -1. Notice that makes kind of a fun graph. Whereas if I go to like there, it's not as interesting of a graph. If I go there, it's not that interesting. So and let's march on this graph from x is -3. Let's march all the way over to 2. to x is 2. Now, can you tell from the graph here, can you estimate about what the answer to that should be?
Like 1.5.
Yeah, you agree with that? Like 1.5. Our y value should be like 1.5. And if you look really carefully, maybe it's even a hair under that, right? We'll keep zooming in. So it's actually a hair over 1.4. You agree with that? If I zoom in on it a little bit. So it's around 1.5. So I'm going to start at x is -3, y is -1. And I'm going to cruise along this graph. And all I want to know is the answer. Now, I think it's cool, as I showed you in Excel, to, get the entire graph, kind of a lot more interesting. And again, maybe let's do that really quick, just since it's not that hard to do. I said -3, -1, x cubed minus 4y. -3, -1. And our slope was found by taking x cubed minus 4 times y. Is this all I need to do? Is this working? Have to change anything else?
I think you also maybe have to drag that formula down to the rest.
Just the
Alright.
slope though, right? The slope's the
just-
only formula I have to drag down. Everything else is fine.
I think so. Yeah.
Except we wanted to go all the way to, I said x is 2, right? So let's go all the way to x is 2. Ooh, I'm pretty close. Got it.
Should we turn in like the file, the Excel file, or do you just want like a screenshot?
Yeah, I was gonna.
All I'm really going to ask you, either one is okay.
Okay. So we could just do them both in the same Excel document.
Yeah, doing both in the same Excel. Just send me something. And in the end, all I'm really going to ask for is that number right there. You see how it came out just what we thought it would? 1.4. Pretty good, huh? And of course, the fun part of this is not to just, to me, that answer is kind of boring. Like, great, you made it to there. But keep in mind, on a practical level, let's just do it this way. Let's say you have a pool and it's growing algae in it. It's like, that sucks. So you decide, I'm gonna drip chlorine into it, 1 eyedropper per hour or something like that. And then your question is, well, what's going to happen 4 hours from now? What will happen? Does it make sense? That's what we're doing here. We're saying, well, what's the conditions 4 hours from now? Well, 1.41. You see what I mean? Like, do I really care what happened in between? No, I'm just saying what's going to happen later on. You see the practical side of this? So now I'm going to grab all that junk and see if we can create the same, just again, to show you the beauty of this. Quickly insert that graph. Did that actually give us everything? No, I don't think it did. Insert. There we go. Isn't that the graph we just saw? Ding, ding, cool. Now, what I want to show you now is, could we get that same answer even in a better method, in a better way? Let's see. I'm sure I can actually do this. Actually, I guess I'm just going to have to tell you this. I've got a new computer and now I don't just realize that I don't have my TI in such a way that you can see it. So I think I'll write it for you just on the, but we won't actually get to watch it in action. That's unfortunate. But I'd like you to see if you can understand the logic of this. Okay. So we decided we were going to start at -3, -1, or you might say f of -3 is -1. And we want to go all the way up to f is 2, right? And that's the question. But let's see if we can do this in an iterative way. In other words, a second ago, in order to do that, since we went from -3 to 2, that's a total jump of 5. And since we stepped 0.01, that's actually 500 steps. We had 500 data points just now, and we had to write them all down. Well, what if we didn't really care about everything that was in between? Again, I'm only showing you this out of interest, like close your eyes and plug your ears and leave class if you want to. You don't need to know this. This is just kind of cool. I don't know if this is going to be lame, but I think I'm going to rig up an external camera really fast. External cameras we have focus issues. Get this to be looking at my TI. External, where are you? External. Upside down. Of course, I can't zoom this, so you get what you get.
I think it looks okay.
Yeah, it's not bad. If you've never programmed this, this is basic computer language. And the only reason I'm showing you this is not because I want you to understand computers, but because I want you to understand the thinking behind it. This is just powerful thinking. It's kind of neat. It's not so much that I want you to be able to program your TI-84, although you're more than welcome to do this with me. It's kind of fun. I'm assuming you've never done this before. So again, immediately interrupt if you're not happy with this. But the first thing you do is you go to the program button. I'm pointing at it right there. It's right below stat, right in the middle, program. You have 3 options: execute, edit, or new. I'm going to do new. And I guess I'm going to name this. I saw a second ago that I had one there in there named Euler. I was wondering if that was the same exact one, but I don't know. I think I'll just name it EUL for shorts, in case it is the same one. I don't know. EUL. And so what do I want this to do? Well, the first thing I've got to do is prompt the user for their initial point and for their step. Does that make sense? So there's a command called prompt. Almost everything you need is behind the program button. So I see that's out of focus, but prompt. So I'm hitting program, IO for input output, and there's prompt. Second one down. Prompt. And I want to prompt the person for a value for X, for Y, and for H. That's what I'm going to call them. So I'm hitting alpha here, alpha X, comma, alpha Y, comma, alpha H. Again, interrupt immediately if you're trying to do this and would like to be able to do it. I do want to give you time.
Where's the comma? Oh, never mind.
Found it right above the 7. Yeah, ask those kind of questions because I'm going to go too fast, I'm sure.
Hey, Doug, where did you get prompt again?
Prompt is in the program button. So I was using the program. If you hit program, there's CTL for control. The next one over is IO for input output. And then the second command down.
Got it.
And incidentally, if you put something in there you don't like, you can always just hit clear. Unfortunately, there's no undo button on your graphing calculator. So if you clear something you don't want, then you don't get to undo it. You got to start all over again. That's really fun. Now, the second thing I'm going to do here is prompt for what I'm going to call L for limit. In other words, a second ago, we started with X is -3 and our limit was X is 2. So that L is going to be my 2 in a minute because that's how far I want it to go. And this will make sense later, but this is line 3 on the program I'm at right now. But I've got to kind of label that line. So I'm going to go back to program, and then I'm already at CTL for control, and down there at the bottom it says label. And I'm going to hit alpha A. I'm going to label this line A. You'll see why in just a second. Now is where it's time to calculate the slope. Well, what did we say the slope was? We said in our case, the slope was X raised to the 3rd power, correct me if I'm wrong, minus 4 times Y. That was our slope, right? So I'm going to store. Store is right in the lower left-hand corner, right above on, STO, stow. And I want to store that in, well, M for slope. So alpha M. So now I have my slope figured out. I have my first slope figured out. And again, think about this as being really similar to Excel. So I have my slope now. I have my original X, my original Y, I have my step for H, and I now have calculated slope. And so what do I do? Now that I've accomplished my first line, my first row in Excel, does it make sense it's time to go get my next values? So what do? Well, I've got to update my X's. How do I get my next X? Well, my next X, I say second or alpha X, and I'm going to add to that my step, which is H. And what I'm going to do then is say, I'm going to store that in X. In other words, I've got a new X value now. So I started at X as say 10, and my step was 0.2. And so I take 10, I add it to 0.2. My new X is 10.2. The cool thing here is I'm throwing away the previous one. Does that make sense? I'm finding the next X. I don't need to even keep track of the previous X. This is how I get my next X value. How do I get next Y value? Well, we said you take your previous Y value and you add it to your step, which was H. Where's H? Multiplied by your wait, something's wrong with that. Your previous Y, what's wrong with that? No, it's not your
Isn't it
previous.
multiplied by your
It's your slope. Thank you. That's what you're about to say. Your step times your slope, right? So you take your previous Y, you add it to the step times the slope, and then that will be store your new Y value. Notice I'm writing the old Y value or the new Y value right over the top of the old Y value. Because again, I'm saying here, I don't care about all the 500 points. I just care about the end one. So do you agree this just gave me my new Y value? My Y value just got bigger. I'm almost done, by the way. There's like 2 more steps, 3 more steps, and I'm finished. Now I've got to decide, am I done? And so under math right here, I'm pointing at math. Let's see, is it math? If. No, I don't think it is math. I think it's back in program. If. I'm not sure. Let me play for a second. Yeah, it's in program. It's if. The very first thing under control, if. I want to say if that X value, and this is where I need math. Right above math, it says test. I'll do this over. I'm going too fast right now. I just want to explain the logic of it. Second math will give me test. I want to say if X is less than that limit value earlier. In other words, I started at X is -3, and I want to check to see, has X made it up to 2 yet? Is it up to 2 yet? So if it is less than that, then this will do the next line. So I'm going to clear that and start over. So program, control, if I want to see, is my X value right above math, it says test, second math. Is my X value still less than the limit that I chose to stop at? If it is, then I actually want to go back and start over again. So this is a recursive program that I'm writing. It's recursive. Now I'm almost done. I just have to repeat the process. So here's where I needed that label A. In other words, if my X hasn't made it yet, then go back to A and start over. Once I have my new X and my new Y, don't I just plug them in and get the new slope again? So now I want to say, go back up to line A. So this is a really basic program. I can't say go to line 3. I got to say go to the line I labeled A. So where's go to? Well, it's also under program. Go to is control, I think. I think it's way down at the bottom. Control under label. There it is. It's right below label. Go to. Go to A. So as long as X still hasn't got big enough, then go back to A. Well, what if it has got big enough? What if I'm done? Well, then I just want to know what that Y value was. So under program, there's a command. This is the last line. Under program, there's a command called display for input output. It's display. Display that Y value. Again, I'm interested in you understanding the logic of this, not just having it. Otherwise, I just email this to you. You're more than welcome to get your phone out and take a screenshot of that if you can see it. Actually, if you want to do that, I'll raise it up a little bit. This is the focus problem it always has.
So the program automatically, if it's not less than L, it just goes to the next line.
Yeah.
Kinda like
in other words,
if
so in other words, you started at X is say 2, and you were going to X is 3. Then you would say, okay, it starts at 2, and then it goes to 2.1, and then it says, is 2.1 less than 3? Oh yeah, it is. Well, then go do it again. And then 2.1 goes to 2.2. Is 2.2 less than 3? Oh yeah, then go do it again. And finally, it'll get to the place, is 3 less than 3? Oh no, well then that means you're there. Okay, if you're there, then just tell me the Y value you just found.
If you want to change the equation that you're testing this for, do you have to go into the code and edit it?
Yeah, you have to go right there and edit it. Now there's fancier ways to do this. There's cool things that you can do. And I'm using the simplest machine on earth to pull this off. If you're a computer programmer person, and I'm not, maybe you've done this, maybe you know Python, or I'm kind of making up computer programming names here because I don't even know any of them. C++. There's ways to do this in more advanced programming languages that do this automatically. But my point is, this is the logic of where these come from. That's what I've tried to do today. I showed you Excel, which is like you have to do it yourself to get it to produce that graph. But it's kind of cool that you can do it, right? Are you a person that sees things online and just thinks, wow, some smart person? Well, it's actually, oftentimes it's not a really smart person. You could do it too. It's not that hard. This is the logic behind how a recursive program works. So let's try this out. And so yes, you have to if you want to reuse this, you got to go change the slope formula. That's the only thing you have to change. So remember our answer came out 1.41, right? So if I say second quit, and I said quit because I was in program edit mode, and now this is a calculator again. If I say 2 times 9, it's going to say 18. But if I hit program, now I have the option to execute, edit, or find a new program. Well, I want to execute it, and I want to execute that first one, EUL. And when I do that, it's basically blinking saying, is this the program you want? And notice it says question mark, what would you like X to be? Well, we said X was it -3? Yeah, -3. It's prompting me for the Y value, -1. Now it's prompting me for my H, 0.01. And then it prompts me for where do you want to stop? We said we wanted X to start at -3, but we wanted to go all the way up to X is 2. Now, remember, it's going to take 500 steps to get there. But I want you to watch. It isn't immediate, but I want you to watch what it's doing. See right up there, there's a little, circling. Notice it's taking some time. It's thinking. It's 500 steps, man. That's something. But this is a really simple machine. This is not a high-powered program. Bam, 1.41. Isn't that cool?
My program crashes when it asks for H.
Yeah,
Not
let's
sure
go back.
why.
Second, quit. Program, edit. So take a second look at mine. Is there anything that's missing or anything that's wrong? If I get closer, it always seems to like not be able to focus. So it's
Oh, I
X,
see.
comma, Y, comma, H, prompt for L, label A, X cubed minus 4Y, store, that arrow, store in M, X plus H, store in X, Y plus H times M, store in Y. If X is less than L, go to A. Notice those commands, by the way, are not all caps. You can't type go to as GO2O. It's a command and it shows up as capital G, but then the OTO is lowercase. So those are commands. That isn't just a bunch of letters. You can't type 4 letters GOTO and it's not going to do that.
Cool. Yeah, I got it.
Isn't that kind of neat? And it's kind of
Nice.
fun to see that you can kind of do this stuff yourself. And as I said before, this is the neat side of really using differential equations to model things. Because it's like I look outside and I say, okay, there's my lawn. I'm looking at it right now. It's like, that's a little brown. I think I'm going to go do something to it. And again, what I'm going to do is I'm going to change something. That's the language of this class. I don't like that. I'm going to change it. What am I going to change? Well, let's say I got a lot of choices. I could change the water, add more, have more water, have less water. I could change fertilizer. Notice I have 2 choices there. I have 2 things that I could change. That's what partial derivatives are for. But we are just looking at single things. And so I might say, well, I think I'm going to add more water. It's kind of brown. That seems like the easiest thing to do. I'm going to start adding more water. And what I'm going to do is wait a week. I'm going to do that. And then a week later, I'm going to, look and see. And in my case, I'm just going to look at it. But if I was a scientist, I'd be testing it somehow, like giving it a number or sorting according to its color. So I'm just going to do that iteratively, recursively. I'm just going to go out there and I'm going to, dump. I'm going to spray water. I'm going to be an old guy and sit in my lawn chair and spray my lawn with a hose. Boring. And for 20 minutes. And I'm going to do that every day. And then I'm going to look and see a week later, what's happening. Well, isn't that what we just did? We said we started at X is -3. We did something. We had a rate of change. We added water to it. And then we just kept doing it until day 2. We started day -3. We went to day 2 and we said, okay, now what do we got? Well, we got 1.4. I mean, isn't that kind of cool? So made a change. That's kind of awesome. So that's the, if you will, the argument for why you don't need to see, the color every single day. I just wanted to see the color at the end of this. So armed with this program, if you will, you could check or do your assignment tonight in like 2 seconds. I mean, isn't that kind of neat? We made this program once and then all we got to do is go in there and modify that slope formula and then it just works every single time. Isn't that amazing? Your mind should be expanded and blown or you're doing something wrong. Now, we're done, but I'm looking at the syllabus here and it tells me, if I remember right, that we're going to 2.2, which is separable equations. So our last day of the week tomorrow, we're actually going to start solving them. We're not going to wimp out. At this point, we've just been saying, can I at least look at a graph? Can I creep along from my original point slowly and actually make a graph of the solution? Yes, I can, but I can't recognize it. Isn't that kind of an interesting part of this? Stop sharing. Let's go back to this really quick. Goodbye. So I look at this graph right here, and I don't know about you, but I stare at that and I think, I don't recognize that graph. This was the x squared minus cosine graph. That was a neat one. I don't recognize that. I don't get what that is. I don't know where that is. And so after today, we're done playing around. Like we're going to go get it. We're going to go find that. And I have to be careful to give you easier differential equations to solve to start with, and then we'll get harder and harder and harder. We're going to sort of solve different types. Disappointingly, there's a lot of these you can't solve. If you just make one up, like I just did, x squared minus cosine 2y, that might not be solvable, or at least not using the techniques in a first class at differential equations. We aren't just going to automatically be able to solve them all. It isn't going to be that simple, but we can solve tons of them, and ones that model cool things in the world too. So that's kind of neat. So that's our goal, starting sort of from now on. The rest of this class is both creating and solving differential equations. Most of the time we'll be solving them. Meaning find that equation right there, that blue equation that models that cool curve. But what we're also gonna, some of the projects and even some of the assignments in the class, we're gonna learn how to write them for ourselves. And one of the cool examples is flow related problems. Like for instance, you think of a lake and there, there's the lake and then this river flows into the lake, but think about the different chemicals that the river is picking up as it, mines its way through the dirt and dropping off in the lake, because the lake is like a dumping ground. In other words, it's, it stops there and maybe those chemicals stay in the lake. Maybe it's doing that in the ocean. Salinity of the ocean, saltiness of the ocean actually increases for that reason. The rain, when it evaporates, it doesn't pick up the salt. So then the fresh water lands up in the mountains and then it drags its way through the dirt, picking up salt, and it deposits salt in the ocean. So the ocean's actually getting saltier over time. And so a differential equation would model something like that. And so we're going to learn how to write an equation that will do that automatically. And so that's a powerful thing. Anytime you introduce like a chemical to a pool, or even like an air freshener into a room or something like that, you change the air that's in a room somehow, you can model how that's going to actually change. And so, we're going to write our own equations for some of that stuff. It's not just solving some random differential equation somebody gives you. It's like learning to write your own, learning to actually model something for real. So it's a very powerful part of what this class is about. All right. We have concluded Wednesday's discussion, and my wife missed out, and I'm not going to let her watch the video later. She missed it. You missed it. And she'll beg me. No. Stay after if you want. Otherwise, I will see you mañana.
All right.
Thank
thanks,
you.
Hey, Doug, I have a homework question.
Please.
For the separation of variables homework. It's question 34, and it's the Newton's law of cooling.
So,
And I just got an answer that doesn't make sense to me.
I like that. That's music to my ears. Somebody getting something and they recognize it doesn't make sense. That is a good thing. Incidentally, do you have a specific question too, Cheyenne? Because he's asking me a question about tomorrow's assignment. So.
Oh no, I can wait.
Okay.
So I guess I could just quickly solve it. I think I can. I'm going to share my screen if that's okay. I hope it works.
Do you have the power to share your screen? If you don't, I'll give it to you.
I believe I do.
I'm going to make you a co-host just to make sure you can.
Oh, once we install a plugin here, I'll do it on the whiteboard. Okay. You'll have to excuse my handwriting, and I will probably use shoddy notation for the sake of time. So quickly, we have that Newton's law of cooling is dt is equal to K times M E, and I'm assuming this is a function of time. So, so they want us to solve by separation of variables. So I think we would get dt over M minus T equals K dt. We integrate, we get negative ln M minus T equals K T plus C. Okay, and then if we solve for that, then would we get e to the ln of M minus T, and then this is to the -1 power, is equal to e to the C, e to the KT, and then this would be m minus t. And then would I keep the absolute value bars and then invert it?
Yes, technically.
Okay.
For the inverted part.
Oh, and then the absolute value bars would go away because I could combine that with the constant.
Yeah, and the other option you have is to, that negative that used to be out in front of natural log a couple of steps earlier, you could give that to the other side. In other words, it's,
Oh,
and then you don't have to do the old invert thing, just to save you some trouble.
right. You're right. So I think I'll remember that for next time, and I'm just going to continue. So
Yes,
because then we
fair-
get,
fair enough.
just because I think that we'll probably get the same result, but you're right, that I could just, I'll remember that because that's helpful. And then we get m minus t, and then I think our solution would then be t equals that constant m minus c e, and my thing is in the way, hold on, negative kt, right? Okay, so
Doing
this is the
beautiful.
solution.
Yeah.
So the problem reads, I'm just literally, my answer is at the end. So I just want to see if it's an error in something that I'm doing. So, okay, I'm going to erase some of this and leave the solution there. So it looks like they say that the initial condition is that the thermometer, which is what the temperature is reading, is 100 degrees. So I think, so, and then they say that after 6 minutes, oh, and the medium is 70, and then after 6 minutes it reads 80. So I think what we're doing is we're just solving for those two constants. So so at t of 0, it's equal to 100, which is equal to 70 minus c e to the negative, well, that would just be 0. Okay, so then this goes to 1. We get that negative 30 equals c, right? Which would make our particular solution. And could I just plug in that 70 now for m, since I know what it is?
Yes. Because
Okay.
that's permanent.
Right. And then, so this is a more particular solution, except we still have that constant. So then I think that's where the 80 degrees comes in. So here's my question is, are the units important? Because we would then write that 80 equals 70, because I think this might be where I got screwed up, but I don't know. Plus 30 e to the negative 6k. Is that what it would be?
That's right. Yeah, because the time is 6. That's right. And now you can solve that for k. And k is
Right.
in this case, k is the percentage at which the cooling is happening. So that's kind of a cool number to calculate.
Okay, that is cool because you can, right, you can just kind of fill in variables and figure it out experimentally. Okay, so then we would get, oh wait, that's not an e. Yeah, no, it is. So we get 1/3 is equal to e to the negative 6k. And then if we do the natural log, then we get the natural log of 1/3. And I guess it's positive, so we can just put parentheses, equals negative 6k.
Doing great.
And then we would get that k is equal to the natural log of 1/3 divided by negative 6, or negative natural log of 1/3 divided by 6.
That's right.
So, okay. So then the next question is, what is the temperature after 20 minutes, right? I'm not looking at it, I'm looking at my notes.
Yeah, that's correct.
Is that correct? Okay, wait, sorry, my alarm is going off. Okay, so I would just take this constant and plug it in here. So when I do that, let me try to